time clock moving in relationship with this clock. Yeah? So it's kind of intuitive to think that f ds is equal to the derivative of f at t0. But then we have to correct for the fact that this time is going at a different speed than this time, right? So what's the ratio between these two speeds? Well, it is p prime. Yeah, so then you multiply them. And there is also a memory rule for this. So if we write derivatives like df dt, and then likewise the tds, you see that this is very easy to remember. It's like these two dt's cancel out. But it's very important to understand that these are just memory rules, right? You can never do algebra with these things because these are just symbols that mean something, that have a definition, right? So df ds divided like this is not a division of a small df and a small ds. We can think of it like that, but it is not. It's a limit process, you know, limit f plus whatever. So you're not allowed to do algebra, but for memory rules, these things are good. What's not seen in this formula is exactly where are we evaluating, right? So it's important that he is evaluated at t0 and that the other guy is evaluated at f0. So sorry, s0. So the full version would be, yeah, df, or another way to write it a bit even longer, if you want this as a function of s, because, right, this is what we have here, right? F is now, sorry, yeah. So this is called composition when you put them together. So you have df composed with t, ds is equal to df dt at t of s times t ds at s. So now both are functions of s. But you see, this gets very long, this expression, right? So it's actually easier to just, sometimes we even omit this parenthesis here. So you think of f, how it depends on s, and then you write df ds is equal to df dt to t ds. All right, but that's one variable, so that's the chain rule. Now the question is, how could this look in several variables? And clearly now it gets more intricate, right? So what we can have here is like we have a t-axis, and then we have some function sending us into an x and y plane. And this function, we can call it u, maybe. And then from here, we have another function f that goes back into a real axis, right? So the simplest situation we could imagine. Okay, so this was the one variable stuff. So now we consider f composed u.
The camera froze.
Where f goes from R2 into R, and u goes from R into R2. Right, so at the end of the day, when we compose these, You know, it's a function of one variable from one variable.
Sorry, it freezes.
That's some derivative in the classical sense. So there's nothing new there. It's just that it passes through this two variable system. So we have to
Sorry, can you hear us?
we have to understand how we can express this derivative in terms of derivatives of f, and now we go into the partial derivatives, right? So we will cook up a formula somehow with partial derivatives. Now, this formula can intuitively be seen. It's not so, well, okay, let me give you an attempt at giving you some intuition about it. And if it doesn't work, then we look at the details of the proof and that's it. But
it have been frozen.
so here time is moving. We have a function u that sends us into several variables. So this is where we started, right? With curves in space. So this just gives us a curve. So if I have a particular point here, then the gradient here, or the derivative, was a vector giving us the velocity, right? So if I have 2 points, maybe green is not good, red. If I have 2 points here on my time axis, separated by a delta t, so delta t is now a small time step. Do you see when I use colors? Is it visible what I'm doing? Is it more visible now? By the way, I'll stop my share. All right, there you seem to be again. Okay, so my computer froze for a while. Do you hear me now?
Do you hear us? I mean, that was the main issue. Okay, well, it seems like the main issue still hasn't been fixed.
Ja, du sitter där ute och lyssnar.
Can you hear
All
us?
right, guys, can you see me now?
We see you.
All right, that's good. So yeah, the computer froze, I don't know. Did you hear me to the end? So the last thing I was saying was that I have a small if I have 2 time points here and a small time step ahead, were you with me until that point? Okay. Oh, Jesus Christ. So where should I get going from all of the 2-dimensional stuff, or as soon as I switch? Okay, we take it from several variables. So this is the one variable situation. It's not so complicated. You have a slope here. You have a different slope here. If you multiply those slopes or speeds, if you want, then yeah. So we want to do the same formula now in several variables, and there are multiple ways of doing this in several variables. We can think of, f is a function. In the most general case, you look at the composition, f composed u, where f goes from Rn to Rm, and u goes from like Rp into Rn. So you can have multivariables in all 3 locations. But we're going to start with the simplest situation, which is that we have one variable here in the domain of u. You go into 2 variables, and then you go back to 1 variable. So that's the easiest situation, because then, all right, so that's what's written here. F goes from R2 into R, U goes from R into R2, and we want to do the composition F composed U. So if you think about it, what happens to the function F of U? So you take a value here, you go here in the XY plane, and then F picks it up and brings it to a C axis. Right, and actually, once we understand how the chain rule works here, all the other cases are not that much different. So this is the most challenging thing. So, right, then at the end of the day, what we have, f composed u, is just a 1 variable function, right? Because here we have 1 variable, here we have 1 variable, and these 2 variables which sit in the middle, they are not seen at the end of the day. So the function I'm depicting here, f composed u of t, that's the same as f parenthesis u of t, where u is a vector. We could write, okay, then we put a bar on top of u for pedagogical purposes. Okay, so at the end of the day, this is an analysis 1 type object. And then I was saying, okay, so what is u? This is where we started these lectures. U is just a function from 1 variable into 2, so it gives a curve. So this is like something flying around in space or moving around in the plane, right? So it gives us a curve. So my objective here at the moment is to give you an intuitive idea of how the chain rule should look in this situation. It's not a proof, but intuition is always better to have than proofs, but both are good. But I'm going to give it a shot. It's not very easy to see what's going on, but also not impossible. So I'm going to try to give you a feeling for this result, and then we'll look at the proof. Anyways. Right, so here we have a curve. It moves around in 2 dimensions, and this sends us to some value here, right? So this could be, the location of a hiker, and f is like the height of a mountain. So then f, and then this is time. So the hiker comes walking here in the xy plane. F gives you the height all the time. So then the walker goes up and down. And f composed u is just the height as a function of time as the guy goes up the mountain, right? So then you want to know how fast is the guy going up the mountain. Well, at each point on the trail of the hiker. This depends on, of course, his speed, but also which direction he's going. If he's going down slope, then of course you will have a negative. You will have a decrease here of the function. If it's going up slope the mountain, this will go up. And if it's going perpendicular to the slope of the mountain, then nothing happens, so he gets 0, right? So somehow we have to involve directions here in this formula. Okay, so let's look at the fixed time point t0. And then at t0, the walker, he has a gradient, a derivative, which is the velocity, right? So it has two components. It's a vector with a length. The length is the speed. The direction of the vector is the direction of motion. Okay, and then, so where is he a little bit later? So if we take a delta t, yeah, which is just a small number, let's say 1 second, and then we jump ahead on the time axis. Where are we here? We're maybe at this point, right? But this we can approximate using the derivative. So at the end of the day, we have that u of t0 plus delta t minus u of t0, so the difference here is approximately equal to what was our notation again for gradient in this sitting? No, I just got well, I mean, this is a vector du dt, the u1, the t, the u2, the t times delta t. Was this the notation I used, or did I already introduce this vector? We often call it just nabla u. Yeah, well, anyways, so this is what we did in the first kind of 2-3 lectures. So whatever you call it, or the notation is, there's a gradient here. I'm going to call it nabla u from now on. So this vector here is what I'm calling like that. Nabla u is the vector, the gradient at the point, and delta t is just a small time step, right? So this thing here, the white thing, will give you, just a bit of a shorter vector along the direction of motion, which is approximately where the guy is going to be a second later. Okay, now what about I'm a bit out of space. Let me move the camera up a bit. Oh, that was too much. Yeah, something like that. Okay, so if we have then f at some point, so this point here, what are we going to call? Okay, this point is just u of t0. If we have plus h, right? Okay, so this is the formula from yesterday, the linearization. So if you have f at some perturbed point, so h is here a vector, h1, h2. So the difference between a perturbation like the value of f at this point and this point can be approximated by df dx times h1 plus df dy times h2, right? This was the linearization formula. So if you have a differentiable function, this is true. So if you want, you can write equality sign here, and then you have to add the small ordo. Okay, but if now h is equal to the difference of these 2 points here that I'm interested in, so it's going to be u of t0 plus delta t minus u of t0. So this is the red point in my graph, and this is the brown point in my graph up there. Then, okay, so h1 here is just the first component of this. And what is that? It's the first component of this vector here, right? So I get so this guy is approximately equal to the u1, the t, delta t, and the second component is the u2, the t, delta t. Okay? So this, yeah, this is the x and y component of this little white vector up there, the displacement. So now I just throw that into my formula here. And what do I get? I get df dx times the u1 the t okay, and then times a delta t. Right, so this we can write as f of u of t0 plus delta t minus f of u of t0 divided by delta t is equal to df dx times the u1 the t plus df y times the u2 the t. So this is approximately equal to, and you know, if we take the limit of this, that's the definition of the derivative of f composed with u, right? So you have a point t0, you add a small time step, then this gives you a new point, you evaluate f at that point, you subtract f at the first point, you divide with the delta t, you take a limit as you go to 0. This is the definition of the derivative. So okay, so if we take a limit, it's reasonable to believe that this expression here is gonna be the derivative, right? But what is actually written here? Yeah? So here we have, well, okay, let me change the notation a little bit. So now u1 and u2, they are the different components of the vector function u. But the vector function u sends us into x and y coordinates. So sometimes when we have a function like that, remember, we just call the first component x and the second coordinate y as a function of t. So there's a bit of collision of notation between the independent variables here and what we call the function name. So let's agree to do that and see how the formula looks like. Okay, so I just changed the name here. So u1 is now called x, u2 is called y. Then this implies I write we likely get, because this is not a proof. This is just trying to provide you with some intuition. So you take a limit here, you then get df composed u dt, and on the right hand side you get df dx times dx dt plus df dy times dy dt. And look, finally, that is a very beautiful formula. And if we go back to where we started, let me see if I can keep the formula in. Okay. Okay, so the formula now we have is this one, and compare with this one. So they look very similar, right? Here we have df dt, the t ds. Here we have df dx, dx dt, df dy, dy dt. So like that, it's easy to remember, but it's also easy to completely confuse yourself what's written here, what this actually means. So a few pitfalls is, I mean, if you remember here, this formula, very shortly, beautifully written like that, actually hides a much longer expression, which is this, because we have to know not only how the formula looks, but where to evaluate the derivatives. You know, this df dt is evaluated somewhere, the tds is evaluated somewhere else. And that's when it's good to have these kind of pictures in your head. Because if you have the picture in your head of what is behind the formula, then there's never any confusion about what thing is evaluated where, because it's not something you have to memorize, it's something which becomes natural. You know, you can't, you know, if you can't swim in air, right? So if you know you're in air, you have to be a bird, and if you're in water, you're a fish. But so you could never evaluate the function f at the point s, for example, because they don't live in the same kind of space. Same here, f evaluated at t0 doesn't make any sense, right? So we are evaluating here at this formula, we have derivatives of f, partial derivatives evaluated somewhere. where is that somewhere going to have to be? Well, we're taking a derivative at t0, so the corresponding point in space is u of t0, and that's the only relevant point we could possibly evaluate something in in terms of f, right? We're not evaluating f over here or somewhere else along the curve. So somehow, without having to write it, the f dx has to be evaluated at this point, x comma y of t0. And at the same logic, dx dt, dt, dy dt, these two derivatives, that's this gradient at this point. So again, has to be evaluated here at t0. So the f derivatives are evaluated here, the t derivatives are evaluated there. Right. So that's one pitfall, getting confused of what's evaluated where. Another pitfall is if you start to think of this as just symbols that you don't really have. If you start to confuse your memory rules with reality. So as I said, this rule here, df ds, is very easy to remember because you have df, the t ds, the two dt's cancel out, and then it's written just df ds. If we do the same trick down here, or use the same memory rule, we're actually shooting ourselves in the foot, right? Df dx times dx dt, okay, that cancels out. I just get a df dt. And then df dy dt also cancels out. I get df dt. So at the end of the day, I have 2 times the derivative of f with respect to time. So the derivative of f with respect to time is equal to 2 times the derivative of, I mean, that makes no sense, right? So yeah, memory rules should be used with caution. It's always important to understand the underlying mathematics, otherwise you get yourself into trouble. Now, right, so this formula here, if we want to write the long version of it, it becomes d dt of the function f composed u at the point t0 is equal to df dx at the point u of t0 times either u1 or x, what you want, dx dt at t0 plus df dy of u of t0 times dy dt of t0. So you see, an expression like this becomes very hard to remember. So that's why it's easier to remember this and have this bunch of pictures in your head so that you kind of figure out naturally where to evaluate what. But anyways, this is the chain rule in the first version of it, let's say. Okay, there is chats here. Okay, so somebody should mute himself. Please, guys, mute yourself because it creates noise for everybody except yourselves when you're not muted. Okay, good. Any questions so far? So then let's look at the lecture notes for today. Since I started a bit late, I'll just go through. Oh, and I forgot to lock the focus of the camera. Okay. Yes, I can show you the last I wrote. How do I do that? Come on. No, I don't, which means I don't see myself really. Yeah, so now you have it here, right? This is the long version of the chain rule. And the short version is this one, df dx, dx dt, df dy, dy dt, or u1, u2, depending on your notation. Okay, so share screen. Right, so he starts off here with the same example as I had, just notation is a bit different. He calls this x of t, x1, x2, and then writes up the theorem. You see here's the same guy all over again, now a bit different notation. So first derivative of f evaluated at x of t times first derivative of x evaluated at t, and then the same for the second variable. So there's some sort of nice symmetry here in this formula. G is just a composed function. All right, so an example of how to use this. So let's take a concrete example. F of x and y is this x squared e to the power of y, and then x is cosine t, y of t is sinus of t. So now we get, all right, so this is the topographical map of the mountain. This is the climber who's lost. He's just walking around in circles. So, right, the condition for the chain rule to hold is that the functions involved are C1 smooth. So continuous derivatives of, for all four functions involved. All right, so g of t is f of x of t, comma y of t. So here we just throw in cosine of t wherever is x written, and y of t, sinus of t, wherever you have a y. So the function becomes this. Of course, we can just differentiate this one as a, immediately once we have it. So that's not the point. Sometimes, I mean, this is, okay. There are many reasons why you would like to do this, have this formula, even if it's possible to compute directly if you have explicit functions. Many times you don't have explicit functions. So the chain rule says, take the first derivative of f. What would that be? That's 2 times x e to the y. And then you stick in, okay, so there we have it, 2 times x and e to the y. And then you take times the first derivative of x. So that's cosine t, the first derivative is minus sinus of t. And then you do the same for the second variable. And here is the thing, right? So now you have a function that involves x and y and t. And that's not possible. This is just a function of t. G of t, that's a function of time. So that's when you have to remember that this is not just x and y. This is x evaluated at t, y evaluated at t. So at the end of the day, you have to stick in cosine t wherever x is written and sinus of t wherever y is written. And if we do that swap, then we get a function here that only depends on t. Okay, so this was a cumbersome way of computing it. Of course, we could have differentiated this one and directly gotten this, and it's an exercise to do it and check that you actually get the same thing. All right, so a proof here, we will do this proof quite a few times. It goes along what I wrote on the blackboard. You just need to keep track of the error term. And now this order notation becomes crucial to understand it. And actually, not only understand it, but kind of get a feeling for it. Because we're going to get some funny order terms here. So if delta I is the difference between xi at the time t plus h and xi at the time t. So go back to my picture. What we have here is precisely this. Now we're talking about this point and that point, right? So I had t0 plus delta t. In the lecture notes here, it's this point is t and this point is t plus h. So my delta t is h here. Okay. Then we know that this difference here, if we divide by h and take a limit, then we get the derivatives of the function x1, x2. So yeah, now you form this object delta with a bar on it. So a vector delta, a small vector. What is this delta bar? Well, it's precisely this point minus that point. Yeah, my red point minus the brown point. And okay, I don't know, should I sit somewhere here maybe so you can, maybe I sit. I'm just trying to sit so you can see the pictures if that helps. All right, so g of t is the composite function, right? So f as a function of t if you want, but that's a bit cheating to say like that. So me on the blackboard, I wrote, I wrote f composed, or f composed t I wrote there, and later I write f composed u. That was what I was calling my functions. But you know, sometimes in physics literature and engineering literature and other like cheating branches of science, you just call f as a function of whatever, even if you have several intermediate functions there. So up here you would just write like f as a function of s, although f is a function of t that in t depends on s. But we try to avoid that because it gets very confusing after a while. Okay, so g of t is just a composition of the two. Now there is a chat. I can't see the chat. Oh, never mind. All right, so then what do we have? We have the function evaluated at this later point. So this is like 2 points on the trail. You divide with h. And that's the same as having f evaluated at the first point on the trail and then the difference between the first point and the second point on the trail, right? So then overall you're at the second point on the trail. And here minus where you were at the first time. And then you use the linearization formula. But here he works with equality. So then we have a small ordo in the end. And what is actually small ordo now? Now it's a small ordo depending on the norm of the perturbation. But the perturbation is this delta. Yeah. And delta in turn depends on h. So here is where, you know, I said you have to get a feeling for this because otherwise it's hard to read. So what does this really mean? This is a small ordo. It means you have a function with a certain decay rate compared to the size of delta, delta 1 and delta 2. But then we also know that delta 1 and delta 2 have a certain size when h gets small, right? So that's the formula he writes here, that small ordo norm delta is the same as small ordo h. Why is that? It's because, so the size of delta 1 and delta 2 is bounded above by the size of h. In fact, the quotient between this and this goes to the derivative. So if this, you know, if this derivative here is 10, then if h is, you know, 10 to the minus 3, this one can be no bigger than 10 to the minus 3 times 10, or times 11 maybe, to put some margin there, right? So the size of delta I is always controlled by h, which means if you have an ordo norm delta I, you automatically have an ordo norm h. And the details of this argument he's leaving as an exercise for the interested student. So do you want me to do the details of that, or should we just leave it at that and move on?
If you like, you could do
once you accept that this ordo term is ordo h, then you take a limit as h goes to 0, and this line, there's a forgotten to divide by h. I just realized now. I've never seen that. Funny. So delta 1 divided, so here it divides with h on every line, and then here it disappears. It should be delta 1 divided by h, of course. And then when you take the limit, you get x1. Okay. I think I skipped the details. Those of you interested can think about this and ask me during lunch hour if you have questions. We're going to come back to this proof, by the way, in the multivariable setting. Now, the good thing with this theorem, which is maybe a bit confusing at first, is that to generalize it to more general situations is actually very simple. So let's now look at the chain rule when we have two variables and then two variables, and at the end of the day, one variable, right? Okay, so now you have t and s, a function u, and now here you have x and y, and then you have a function f, and you land in a real axis. Okay, so f goes from R2 into R, u goes from R2 into R2, and let's write u of s, so this is vector t comma s, this is reverse order with the alphabet. But anyways, as before, let's call the first coordinate of that x and the second coordinate of that y. Okay? Is it visible? What's going on? Oh. Yeah. Okay, so then the composed function, which we can call g, as a function of t and s, now f composed u, which is equal to f of x t comma s comma y t comma s. So now we want to compute derivatives of g in terms of s and t using, I'll stop this share here. Oh, wait. Are you writing jokes here to yourselves? All right. Now, where was I with this? All right. So we want to differentiate here g. So what does it mean to differentiate g? Well, the only thing we have so far is partial derivatives. So we can compute the partial derivative with respect to t or the one with respect to s. But if you look at it, so how do we do that? If you want to compute the partial derivative with respect to t, then we freeze s, right? And once s has been frozen, so let's say we take some value s0 here, and then we just look along this line. Well, this line is mapped by u to some curve, which is then mapped by f back here. So we're back in the situation I just described before. This is actually just computing a one variable derivative where we just pretend that the s derivative doesn't exist. So if we use the previous formula we had, we get then dg dt should be equal to, well, what was the formula? It was df dx evaluated where? Well, of course, wherever we are at that point times dx dt. And then we had to do the same for the second variable. All right? That's all there is to it. If you want to write this out, the long version would be df dx u of t and s times dx dt at t and s plus df dy evaluated u of t and s, and then dy dt evaluated t and s. But this gets just too long to see what's going on. So I mean, this formula is the most beautiful. If you can just keep in mind where things are evaluated, this is the way to go, I would say. So why can't I hear when you speak? That's annoying. Let me see if I have the volume on. Volume is on. Speakers. Try to say something now. All 44 at the same time.
Hello, can you hear us?
Yeah, now I can hear you. All right. So there was just a technical error on my computer here. Good. So do you want to say something? No, I thought so. All right. So here, yeah, all right. This is more or less precisely what I said. So, well, yeah, it's the same formula, it's just different notation, right? So the theorem says if f is differentiable and the u1 and 2 of S and T are partially differentiable, then G is partially differentiable and the chain rule holds. So note here, differentiable is the stronger thing. To be partially differentiable is a weak thing. Differentiable means that this linearization, this tangent plane, is a good approximation in every direction. Partially differentiable just means that you have partial derivatives at the point, right? So that was kind of the essence of last class, to understand the difference there. Okay, so let's look at a quick example again. F of x and y is sinus of x squared y squared, but x and y are in terms functions of s and t. So then we form the composite function and look at, for example, the GDS. Then we take our formula here, differentiate f with respect to x, we get this, and then x is differentiated with respect to s. So we go up here, okay, we differentiate with respect to s, the t squared remains, so then you have the t squared here, and then you do the same in the second variable. And now you have a function of x, y, t, and s. And that can't be, we just wanted a function of s and t. So this is now where you have to say, aha, but we're dealing, f has to be evaluated at the point in the plane corresponding to where we are in s and t. So the formula I have here for x and the one for y is what you have to plug in up here, and then you get an expression that only depends on s and t. So actually today is a bit of a short class. So this can be used in a funny way to solve partial differential equations. Partial differential equations is like one of the big fields of mathematics. So most equations arising in physics involve functions and their derivatives. So an equation involves like x and y and c, maybe like variables, numbers. So then you can write x plus 2y minus 3c equals to 0, and then you can think about how many solutions do I find to this equation. Or you can have equation systems also, so you have several equations. But the point there is we're looking for a number. What comes out of our solution is a number or a triple of numbers, something like this, points. In physics, you often want to find actually functions. So the unknown variable is not a number, it's a function. It could be, for example, the heat distribution in a room, the future temperature of the planet, whatever. So the solution, what you're looking at, the stock market rate in the future, also a popular function to try to find. So what we're looking for is often functions, and an equation involving an unknown function and its unknown derivatives is called a partial differential equation if you are in several variables. If you're in one variable, it's called an ordinary differential equation. So we have two courses, I think, in ordinary differential equations and also one in partial differential equations. It's a big field of study. So here we're just going to touch the surface a little bit, and for you to at least get a feeling of what these things are. So let's have a look at this. U is the unknown function. We don't know what it is. We want to find it because we have figured out by some laws of physics that our U need to satisfy this equation here. So x and y are the variables, the independent variables, like, so this is a function in the plane. And u as a function of x and y is what we're looking for. And then we can compute the first partial derivative and the second partial derivative. And for whatever reason, we believe that if we multiply them like this and take this difference, we're going to get 0. Okay, what function can satisfy that? Now, you realize that this is a difficult question. So usually when we have normal equations just involving numbers, that's a difficult question. So here, it's how it is. So most partial differential equations, most of them can't be solved. Of course, you can go to numerical theories and find approximate solutions. You can do mathematical proofs like existence of a solution. Even without finding it, you can just say, well, it exists and it's unique. Things like that can be good, because if you have a computer that computes some sort of approximation, if you don't know that, you know, what you're looking for actually exists, then the numbers the computer give can be completely pointless. So like that, abstract math or theoretical math play a role. But partial differential equations where you explicitly can find the solution, write it up, you know, as in our school books. U of x and y is x squared plus y squared plus something. You know, that's rare. But still, anyways, so yeah, we're going to look at techniques of how to find such solutions. Yeah, so here's one way of doing it, or no, not one way of doing it, but here's just look at this and you see if you follow. Okay, so you can sometimes solve them by moving to a new coordinate system, right? So the last situation here, we have s and t and x and y. Can be thought of as a change of variables. Just like in the first example I had today, when f depends on time, but time is different in two frames. We had also the s time and the t time. It's here, right? So s and t can be a coordinate system in the plane such that when you map this over, these are geodesic straight lines here, you get some curved things in the XY plane. And then these are like the sort of straight lines in the new coordinate system, right? And here is where this other book we have for the course, Callahan, is excellent in kind of visualizing these transformations in several variables. So I'm going to put that up on the schedule, like relevant sections that you can just read at your own leisure. Yeah, because visualization is really good. Now I'm sitting in front of the picture and saying that it's important to visualize. But so here we have an equation system in the XY coordinate system. We have no idea what it is, how to solve it. And of course, to come up with a clever change of variables so that the solution becomes easy to see is almost impossible. So these exercises, they always go like this, that whoever constructed the exercise tells you already that if you do a change of variable like this, you will then see the solution. And you will see in a little while what C means. So change of variables, again, looking at this picture here, you already know one of them quite well, which is polar coordinates, right? So T and S could be actually radial distance and angle, theta, and X and Y could just be X and Y in our usual plane, right? In that case, the geodesics would be circles around 0 and straight lines emanating from 0. So sometimes things look better in polar coordinates than Cartesian coordinates. We know this. Okay, so the question here now is technically, how do we work with this? So if I introduce new variables s and t, how on earth am I going to transform this equation into a new equation in s and t? So so here there are a few dogs hidden, så säger man kanske inte på engelska, but that's a Swedish expression. But some buried bones or whatever. So first, in order to make an inverse function in several variables, of course you have to check that the inverse exists. And here we just jump all of that. So if we call so the function in s and t coordinate system that at the s and t coordinate has the same value as the corresponding value for u in the x and y system, right? So u lives here. At each point, it has a value. And then there's a transform going back and forth between these coordinate systems. So this point here corresponds to that point there. Then you let v, the new function you introduce here at this point, have the same value as the function u has at that point. Yeah? So again, this in some applied material, they would not even change the name for it. But I think it's better to change the name. So now x and y are related through this formula. And if we want, we can find also the inverse formula, how x and y depends on s and t, to really make sure that this is a valid change of variables. We need a bijection here. But we don't do that now. We just try to learn how to work with this. So now I want to compute the u dx. Okay? So u, I can think of it as the function v, as a function of s and t, and then how s and t depends on x and y. So, right, this is what I have here, d dx of v of s of x and y and t of x and y. And now we use the chain rule. So this is dv ds, ds dx, dv dt, dt dx. And all right, so the s dx and the t dx, this I have explicitly. So this I can actually compute. So then I get 2x plus, yeah, okay. So in both cases, the derivative is 2x. And then dv ds, dv dt are unknown, right? I don't know the function u, so I don't know the function v, but if I find v, I immediately find u, and vice versa. So we are just doing this change of variables in the vain hope that things will look better in the new coordinate system. So we do the same with the second derivative, and then du dy becomes 2y dv ds, and now a minus, the minus coming from that, here there's a plus and here there's a minus. So there's a difference here. Okay, and then we go back here. So now we can stick in the u dx and the u dy in here. And you see that then this y will hit here. So you get a 2xy and a 2xy. And the same, this x is going to hit here. So you get 2xy, 2xy as coefficients here. So you see, there will be some cancellation. So if you do the math slowly, it goes here. At the end of the day, you have 4xy dv dt. So dv ds there's a plus here and there's a minus here. So it canceled out. All right, so now this equation still, if you've never seen partial differential equations, you don't know how to solve it, but it looks certainly better because we just have one partial derivative as opposed to two. Okay, so here x and, so this should be equal to 0, right? And x and y, these are just variables. So the only way that this is going to be 0 is if the v dt as a function is identically equal to 0, because these ones are just 0 at points, but as functions, variables, they are not 0. So for this to be 0, we need the v dt to be 0. So what is this equation actually telling me? It tells me that the derivative in the t direction, this function living on top of the st plane, if I differentiate it in the t direction, it's 0, so that means it's flat. Nothing happens in the t direction. But if I take a different s value, then again, it's flat in the t direction at some constant value, but that constant value can be different here and here, right? So there must be some function phi, just telling me what constant I have on each line of t, such that v of s and t is actually just equal to phi of s. So it only depends on s, it doesn't depend on t. So at the end of the day, we get that u of x and y is equal to v of st, which is phi of s, and s, we know what it is, x squared, y squared. This comes from the, s here is x squared, y squared. So basically what do we have here? Well, this is the radius square. So we see that the functions that solve this equation, the original one, are radial functions. So here's another thing with partial differential equations. The solution is seldomly a function. It's just a class of functions of a special type. So if you have the wave equation, it describes waves. You don't get like one wave out of that, like, okay, this is the one existing wave and it moves to the left. No, you just get functions that behave like waves. And there are many different waves and they can go in different directions and so on, right? So solutions to partial differential equations are always like classes of functions, a function with a certain type. Here we have a one variable function that depends on the radius square. So this, if I were to paint it, so phi could look like this. And then phi of r squared will be constant on circles around 0, and the value is going to be whatever r squared evaluates to here. So if we look at it on this line, it's going to kind of look maybe something like that, the profile of it. We have this square, so that will stretch it out a little bit. And if I take a different function, then I get here a different profile. But the common denominator is that both are radial, yeah? So this partial differential equation that we're solving, maybe it's describing the water pattern at the snapshot if you throw one drop into still water. So waves goes out in a radial fashion. Each time you drop something, the wave may look different, but it has the common denominator, all waves, that there's a center and then there is a circular pattern. So that's what we got out of this calculation. All right, this jumped up level of difficulty quite a bit. The key message of today's class is not how to solve these partial differential equations, but that is a funny task, and we usually throw it in on the exam as well. One exercise of this type. So, before the exam, we will look at it on Friday also. Yes, but what else did I want to say? Yeah, but the key message is just go and understand the chain rule. This was an example of how to use the chain rule and for you to somehow connect to, reality a bit, like what is the purpose of doing this, all of this math. Here's another example. The example has some errors, so, well, look at it if you want. To wrap up, if I'm just going to give you the formula for the general chain rule, and we're going to look at the proof for this formula next time on Friday. But okay, so how can we make this more general? Well, f can go from Rn into R. Actually, here we could have a vector as well, but that really doesn't add complexity to the question. But instead of 2 variables here in the middle, we could have, 15. And then U is a function that goes from 10 variables into 15, and f picks up 15 variables and sends us into R. So then the composite function G, which is f composed 2, takes 10 variables into 1. So how would our formula look like now? And here's the theorem. All right, so f needs to be differentiable. The UIs need to be partially differentiable. And okay, the fact that there are m UIs is not complicating at all, because just like what we saw here in the 2 variable situation, if you want to do one partial derivative, you just freeze all the other ones, right? So you just can think of them as not even being there. So the question is, what happens with this intermediate here? So the G, the T, 1. Okay, so we differentiate with respect to the first variable. And here we have f depending on U1, depending on T1, and then these other guys that are frozen, ... up to UN, depending on Tn, and these guys that are frozen. Well, yeah, the formula is the best we could hope for. It's just a direct generalization of what we had earlier. So you take the first partial derivative of f, multiply with the corresponding partial derivative of U1 then. And then you do the same with df du2, the T1, because this T1 is fixed, right? And then you go all the way up to UN, the T1. Add them up, and that's the formula. And at the end of this lecture notes, it talks a bit about functions that are homogeneous of degree something. There's also a small section of that in the book. I don't find this very interesting, and I think there's enough material for you guys anyways to dig into. So read this if you want, but it's not part of the main curriculum here. Okay, so with 1 minute to 10, that's it. On Friday, we have a flip in order. So you will have the seminar first and then the lecture, because yeah, I have to do something in the morning. I hope I will be on time, but well, if I'm not, at least I will post it on Canvas, but it shouldn't take me more than, yeah, so I should be able to be back here at 10 if nothing goes wrong. So yeah, that's it. Any questions? Otherwise, remember that today between 12 and 1, I'm available on Zoom, on this Zoom link, to answer, any sort of questions about, either the setup of the course or how to prove things, or, well, whatever's on your mind. So feel free to tune into that, and over and out.